if people want.
Perfect, thanks.
Okay, so I like to think of exoplanet science themes as being in three broad categories. So one is just demographics of planets. So, where planets live in the parameter space of mass and period of the planet, or radius and semi-major axis, and also, where kinds of host stars that they orbit. Just kind of a rough census of where exoplanets live and what their distributions are. And then second is a detailed characterization of individual exoplanets and exoplanetary systems. And obviously, if we can get detailed characterizations of systems as well as broad demographics of those same systems, that's the ideal. Although, because of the nature of our detection methods and characterization methods, that's not generally possible for all kinds of planets that we detect. And then sort of, I think we can all agree that, kind of the holy grail of exoplanets is looking for habitable worlds and potentially evidence of life. And of course, our understanding of the demographics and characteristics of exoplanets inform the last science goal. Okay, so let me just talk a little bit about demographics. So this is going to be very, 10,000 foot view of where we are now with demographics and where I think we're going. And so I'm going to just do this in the context of the typical planet mass versus semi-major axis plot. Obviously, there's other axes that we care about, other properties of the planet, the radius, period, but also this host star mass or metallicity and other things like that, binarity. So it's impossible to show all those different axes. I'll just focus on this one. And then what I'm doing is I'm drawing extremely approximate regions of this parameter space where different surveys and or methods are sensitive. So ground-based surveys are largely sensitive to, wide-angle ground-based surveys are largely sensitive to giant planets at relatively close separations, although specific surveys like Speculoos and Mirth are sensitive to lower mass planets around lower mass stars. Radio velocity has this kind of detection sensitivity threshold. Of course, where you are depends on how precise your radio velocity is and how long you've looked. But this is just kind of a rough sketch of where we're sensitive to. So again, not surprisingly, sensitive to close massive planets. This is roughly the region of Kepler. So this down here is set by the signal to noise requirement for a typical star in Kepler. And this is just the requirement for 3 transits. This is very roughly what we have from ground-based microlensing surveys. This is, can go down a little bit lower with the sort of current MOA and KMTNet surveys. Free floating flat planets with ground-based microlensing, we're sensitive to those. Probably maybe down a little bit lower than I'm showing here, but again, these are free floating planets. And then direct detections are largely sensitive to young planets currently from the ground that are separated, relatively largely separated and relatively massive. Okay, so that's all pretty familiar. And so now I've just drawn in sort of by eye where I think future, current, and near future surveys are gonna have sensitivity. So I've added in TESS. One important thing to note about TESS is it's not actually covering a region of parameter space in terms of mass and period or radius and period that hasn't already been covered with Kepler, although it's looking at many more stars. So it's not going to find qualitatively new populations of planets, but may find oddballs that we wouldn't see because they're on the tails of the distribution. And actually, Plato is really not very much more sensitive in terms of the parameter space than Kepler will be, depending on exactly what their survey strategy is. If they do focus on the Kepler field for a couple of years, then they can extend the sensitivity of the Kepler field, and that's kind of what I'm showing here notionally. I'll talk about space-based microlensing with Roman here. We can see that gives you a very broad region of parameter space, including very low mass free-floating planets. And so that kind of, these surveys, once Roman and Plato and Kepler are all combined, will have a very broad census of exoplanets with separation masses and radii greater than roughly that of the Earth, and basically all separations. But there's still future potential for things that may or may not happen. So one is if you can get sub-microarcsecond astrometry. So think something like what SIM was supposed to do, or the Theia mission concept and ESA, or European Theia mission concept, that would have sensitivity here. I just note here, I forgot to mention, this is Gaia. Gaia, again, is not really sensitive to new planets in a new region of parameter space, but obviously it can measure properties of planets that you can't measure elsewhere otherwise, like mutual inclinations, and may have sensitivity to more systems. So again, might find some oddballs. But some micro-arcsecond astrometry allows you to get down to sort of Earth mass planets at sort of Earth-like separations around sun-like stars. But you're limited, of course, by the duration of your astrometric survey. And that's a pretty sharp cutoff for most cases. If you can get sub 10 centimeter per second EPRV, which people are working very hard on, you can get actually quite down to quite low masses, again, including Earth analogs around sun-like stars. And then future direct imaging surveys from space like LUVEX, LUVAR, HABEX would give you a region of sensitivity here. This is set by the inner working angle. This is the outer working angle. And this is basically their contrast curve. Again, these are very approximate. So, you know, in the more distant future here, sort of 20, 25 years from now, when something like LUVEX flies, we'll have really kind of tiled this parameter space pretty well. And I think what's important to note is there's a lot of overlap, which allows you to check for systematics and these demographics. And because these different methods are sensitive to different kinds of parameters, you can learn some complementary information. So I think the prospects for demographics are actually quite bright, and it's something that I think we'll have a pretty good handle on even in the next 10 years after Roman. Okay. Quickly moving on to characteristics. This is obviously could be many talks in and of itself, so I'm just going to be relatively brief. So first, you know, we like to measure masses. Masses we think are one of the fundamental properties of exoplanets. We don't have very many tools at our disposal to do so. And for nearby stars, basically we have radial velocity and astrometry. So we have current EPRV telescopes, or sorry, instruments, including a sort of new next generation that have recently come online, like, and I'll mention those here in a little bit. We can imagine future EPRV sub 10 centimeter per second, maybe something in space like the Earth Finder concept led by Peter Plavjan, that might give us sensitivity to low mass planets. And astrometry, you know, we have Gaia, and then in the future, maybe a sub micro-arcsecond astrometry mission. We can measure masses with transit timing variations as well, for transiting planets only, obviously, in multi-planet systems. We'll get a lot more of those with Plato, for example. And I'm not mentioning here microlensing, but microlensing can actually measure masses of individual planets as well. But those are generally not going to be nearby, and they're not systems that we're going to characterize in great detail. Okay, and then in terms of characterizing atmospheres, and so obviously when you measure masses of transiting planets, you can get interior constraints on the interior structure, as we well know. In terms of atmospheres, we have quite a few tools at our disposal: transit and eclipse spectroscopy, phase curves. This can be done from ground-based telescopes for certain kinds of planets. And of course, we've seen with Spitzer and HST tests, and then soon with JWST being able to do these kinds of measurements. And in the future, we have missions like Twinkle, Plato, and Ariel will be able to do this as well, obviously for different wavelength bands and different kinds of planets. Direct imaging is one of the best ways to characterize the atmospheres of planets. So we can do this with ground-based telescopes for the planets we can detect today via direct imaging. We'll be able to do this for some planets with Roman CGI, and then something like LUVEX, of course, will do this for a fairly broad range of planet properties and start doing comparative exoplanetology of the atmospheres of planets with a wide range of masses and separations. And I'll also mention here the ESA mission proposal LIFE, which is a mid-infrared interferometer. And then, you know, there's other methods we have as well. I'll just mention high resolution cross correlation, which is shown to be a fairly powerful method of directly detecting planets using high resolution spectra and high signals noise. And that in the future, we can imagine doing this with ELTs, for example. And that'll give us access to a whole suite of planets that we can't do today. I think, you know, we like to focus on habitable worlds in search for life. As I said, I think we can agree this is where the field is going. So I like to say there's two paths you can go by. This is an oversimplification, but the two paths are temperate terrestrial planets around low mass stars and Earth-like planets around sun-like stars. And because of the nature of the detection techniques and characterization techniques that we have at our disposal, they naturally fall into sort of surveys for planets around low mass stars and surveys for habitable planets around high mass stars. That's obviously an oversimplification, and I'll mention some exceptions there as well. So I like to think of these two paths as pale blue dots, Earth-like planets around sun-like stars, and small black shadows. So for Earth-like planets around sun-like stars, it's direct detection and characterization. For temperate terrestrial planets around low mass stars, it's transit spectroscopy, transmission spectroscopy, to look for biosignatures and evidence of habitability. So the easiest path, the path that we have at our disposal now, is the small black shadows. A lot of this has already been done, and we can really look forward to a lot of it with a lot of exciting results with JWST. So the idea is you have this tiered strategy where you find the planets with something like Mirth or Test or TRAPPIST or Speculos. And the TRAPPIST-1 system is obviously one of the best examples of this. And then you go and you can try to characterize those planets using transmission spectroscopy or eclipse spectroscopy or phase curves. We can do some of this from current facilities, but JWST promises to revolutionize that. And we have some chance, depending on who you ask and how optimistic or pessimistic you are, have some chance of characterizing potentially habitable worlds around these low mass stars, and maybe even looking for finding evidence for biosignatures. I'm not going to wade into that debate because it's not really my field of expertise. And of course, the second pale blue dots is just directly resolving an Earth-like planet relative to a sun-like star. The difficulty there, of course, is your contrast is the flux ratio is about 10 billion, and for something at 10 parsecs, it's separated by 0.1 arc seconds. So you have to suppress the light from the star by one factor in 10 billion, all the way down to 0.1 arc seconds, and that's the challenge that we have. But if you can take the spectrum of that pale blue dot, which is going to be about 30th magnitude in V for, again, a typical system, you can look for evidence of habitability via water vapor or Rayleigh scattering, and evidence for potentially life through oxygen, for example. And again, I won't enter into the debate about how about false positives and false negatives that we can get. That's obviously a very important thing that needs to be studied. It has been studied, needs to continue to be studied. Okay, so I mentioned that was an oversimplification. These are the other two paths we have. So with ELTs, we can probably do direct imaging of habitable planets around nearby M stars because the contrast ratio is better. But obviously the separation is smaller, but with ELTs, we have a smaller lambda over D. Of course, this requires adaptive optics. We can do mid-IR imaging using ELTs. So this is, and in this case, you care about, you'll be able to, the best targets are Earth-like planets around sun-like stars at 10 microns. And because you need the angular separation in that case. And in thermal infrared, the Earth to sun ratio is more like 1 part in a million rather than 1 part in 10 billion. So it's possible we could do that, likely only for a handful of systems. You can imagine emitted infrared interferometers in space. That's another path that is being explored, I think, mostly by ESA through the LIFE mission concept. You can imagine doing high dispersion coronagraphy or high spectral resolution cross correlation to look for things like oxygen in Earth-like planets around sun-like stars, where you're not actually resolving the planet, but you're looking for the Doppler shifted features of oxygen or something like that in the atmosphere. Okay, so those are the kind of tools we have at our disposal. What are the missions and telescopes that we have coming online? There's obviously a lot of them. It's actually quite amazing if you could just sit and try to list missions and telescopes that have significant exoplanet applications. That list is quite long. So I think there's a burgeoning future for exoplanets, which is great. Obviously the next great thing that we're just waiting for is JWST. So far, everything is going on with flying colors. There's lots of things you can do with exoplanets with JWST. I'm just focusing here on transmission spectroscopy of temperate terrestrials around low mass stars. And this is actually a simulation of what you might see with JWST. Actually, this is from the Origins report, but there's many, many, many other examples of this. And again, I'm not going to debate as to whether or not this is optimistic or pessimistic, but just gives you an idea that with transmission spectroscopy, you look for features like methane, carbon dioxide, water vapor, ozone, etc. Okay, so anxiously awaiting that. In terms of mass measurements and EPRV, EPRV, I am personally convinced will always be important as an important tool in our arsenal of detecting, characterizing, and measuring the masses of planets. And quite recently, we've had a sort of number of next generation EPRV instruments that are built and have been commissioned. So for example, Express in the 4.3 meter in Arizona. There's obviously WIN and NUID, HARPS 3, KPF, which is I think being commissioned now. Someone else probably knows better than I do. And then in the future, we'll have EPRV instruments on things like, I forgot Maroon X, which has delivered some great results. I mean, all of these that have delivered results have been great. And I realize here I'm missing some things like the Habitable Planet Finder. I apologize if I missed your favorite EPRV instrument and telescope. And in the future, we can imagine things like EPRV instruments on the ELTs, the large segmented telescopes. So I think there's a lot of potential there. Of course, the concern is to get down to sub 10 centimeter per second to really get Earth analogs around sun-like stars. And that means really controlling not only your instrument systematics, getting enough photons and cadence, but also being able to suppress the stellar variability or mitigate the stellar variability, which is going to be of order meters per second rather than 10 centimeters per second. As I mentioned, I was co-chair of the National Academy of Sciences Exoplanet Science Strategy, and we, our committee, emphasized the importance of continuing to develop EPRV as an important tool for characterizing exoplanets and measuring their masses. So our recommendation was that NASA and NSF should establish a strategic initiative for extremely precise radial velocities so that we can get down to these precisions. And why NASA and NSF? Well, NASA is really good at project management, which is, and this is would be a pretty broad and extensive project. NSF is good at dealing with ground-based facilities. So together they really are complementary and are required to get this done. I won't go through this. We published a report from the Extreme Precision Radial Velocity Working Group that kind of outlined why we thought that this strategy was what this strategy would look like. This kind of broad survey using new telescopes or new instruments that could enable us to get to Earth-like planets around sun-like stars. And you can find it on the web. I'll skip that. Okay, so I will mention, though, unfortunately, this was not specifically called out in the Astro 2020 Decadal Survey, although probably that the main reason for that was likely that it was probably too small of a project, at least in the eyes of the steering committee, to be prioritized. But there's still some effort to actually try to see if this initiative can actually get going. And it's an important precursor science for things like LUBEX, which I could talk about if you'd like. Okay, so not everyone knows about Twinkle. Twinkle is actually a private mission that individual institutions or individuals can buy into. So Ohio State is one of the founding members of the Twinkle Science Consortium. And so this is a relatively small 0.45 meter telescope dedicated to doing optical and near IR spectroscopy from 0.5 to 4.5 microns at relatively low resolution. And the main science goals here are characterization of transiting planets and also solar system applications. And there will be a survey design of certain targets that is going to be decided upon by the main science collaborators. And so you can think of this as, as a good application for the low-hanging fruit of the transiting planets that are just way too just overkill to do with JWST. And so rather than use precious JWST time on giant planets, transiting planets, for example, where you don't need that aperture, but you do still need to observe during the whole transit and before and after. So you're basically wasting photons with JWST. That should be offloaded to something smaller like Twinkle, and JWST should be optimally focused on the small temperate terrestrial planets where you need all of those photons. At least that's my opinion. And Ariel will do some of this as well for large planets, but Twinkle will come before Ariel. Okay, and this is just an example spectrum of what you would see with three transits for HD 209-458b with Twinkle. So you can see this is the wavelength range of WIFPIC3, and this is the full wavelength range of Twinkle. So you can see we can detect the features in the atmosphere like water vapor and methane. Okay, so I think most people in this audience are probably pretty familiar with the Roman, so I'm not going to go into it a lot. I'm spending a lot of my time on Roman, as have many other people. It's exciting because it's actually being built now, and it's actually going to happen in launch in something like 4 to 5 years. And so it's a real thing. As most people know, it's basically Hubble in terms of aperture, but with 100 times the field of view. And that allows you to do survey broad area, and it's basically optical to near infrared, so 0.6 to 2 microns. And that enables you to do broad surveys of the sky relatively quickly, or smaller surveys of the sky repeatedly. And it's kind of the latter that is of interest for microlensing surveys to give us the demographics of cold, low mass planets. And of course, it has a technology demonstration instrument, CGI, which is going to be the first active chronograph in space. And that's going to retire a lot of the technological risk that makes missions like LUVEX possible. And so that's very exciting as well. And it will do science, some science, although exactly how much science depends on how well it does relative to its specs. So very complicated instrument, very impressive. Again, I'm sort of preaching to the choir here, but I'm very excited about this. And in terms of the sensitivity, these are the kinds of requirements up here in terms of flux ratio versus separation, but these are the predicted. And you can see we're starting to get into mature Jupiters around the nearest stars, which is super exciting. Okay. And then the wide field instrument, again, we have all the detectors, they're in place. There's quite a few filters from sort of 0.5 to 2 microns, including a wide filter from 1 to 2 microns that is used for the bulge variability survey, which will, among other things, use microlensing to detect cold planets, cold low mass planets. So I and the rest of the microlensing science investigation team worked really hard to develop a kind of notional survey design, which we call the Roman Galactic Exoplanet Survey. You can think of this as just one possible realization of the bulge, sorry for the misspell there, bulge time domain survey, which is one of the main core community surveys that will be done with Roman. So our survey design, which we sort of optimized for Earth-like planets near the Einstein ring, is about 7 fields for about 2 square degrees, 15-minute cadence, observations and other filters to get colors of the source stars, a total of 6 72-day seasons. So that's 432 days spread over the 5 years of the mission. And with the first 2 seasons being the first 2 seasons that are available for Roman, and the last 2 being the last 2 available at the end of the 5 years. And so there's lots of work that's been done on this, but I just want to call out in particular Matthew Penny and Samson Johnson, who have been largely responsible for the predictions for the yields of Roman for bound and free-floating planets. And so, we don't really know what we're going to find, but our best estimate is we're going to find a lot of bound cold planets, maybe 1,400. We'll have sensitivity all the way down to the mass of Ganymede, at least at the sort of optimal separations you can see here. Sensitivity analogs of all the solar system planets except for Mercury, hundreds of free-floating planets, maybe even more if the recent estimates of the number of free-floating planets from ground-based microlensing surveys are true. Sensitive to lunar mass objects, so moons around Earth-like planets and giant moons around Jovian planets, and 100,000 transiting exoplanets, and then a whole host of other science like the black hole mass function that is not necessarily related to exoplanets. Okay, and then we have the giant segmented telescopes that will be coming online next decade, hopefully. And there we have a lot of things we can do with those. So we can characterize planets using transit eclipse spectroscopy. We can measure masses using extreme precision radial velocity instruments. But I think the real kind of excitement there is that we can do direct imaging of planets that are relatively uniquely done by ELTs, like reflected light in the near infrared or visible of temperate terrestrial planets around M dwarfs, or thermal imaging of Earth-like planets around sun-like stars for a handful of systems. So that will be quite exciting. Okay, and I won't go through these figures. I just point them out for reference. In the exoplanet science strategy, the members of the survey of the committee, in particular Dimitri Maouet and Bruce McIntosh and the other people listed here, worked extremely hard to come up with kind of estimates for what ELTs would be capable in terms of direct detection and characterization of exoplanets. So I encourage you to go look at the chapter of that report for what we can expect from ELTs. Okay, so now I'm just going to pivot and talk about the large mission concept studies that were carried out towards the end of the last decade. And so there were 4 mission concept studies that were carried out between 2016 and 2019, which were eventually called Lynx, LUVOIR, HABEX, and Origins. These studies went on for about 3.5 years. The final reports were due in August 2019, and all 4 mission concepts briefed the EOS and EOS 1 and EOS 2 panels of the Astro 2020 Decadal Survey in October of 2019. And these mission studies were somewhat unique. So what were they? They were science and technology definition teams that were drawn from universities and NASA centers that were tasked to come up with mission designs at a reasonably detailed level that could accomplish some set of science goals to be outlined by the teams themselves. So there was each of them were based at a NASA center. So HABEX was based at JPL, LUVOIR and Origins was based at Goddard, and Lynx was based at Marshall. And we also had participation from international representatives, non-voting members, and aerospace industry working groups as well. So this is very much a team effort by a lot of people, and a significant fraction of the whole community, not just exoplanets, were involved in these studies. And they were different from previous sort of mission concept studies in a number of ways. So the goal, of course, was to provide, the best possible mission concepts to the Decadal Survey so that they could realistically evaluate whether or not the science that was advocated by these teams was actually doable with the technology proposed, figure out what technologies needed to be developed, and have the best possible estimate of what the actual cost and timeline and risk of these mission concepts were. And so that meant developing these mission concepts, the science in tandem with the technology at a level that was incredibly detailed. And so these were some of the most detailed, maybe the most detailed mission concepts ever proposed to the Decadal surveys. And that I think was actually quite important in them getting prioritized at the end of the day. So they were complete and mature concepts. They had, science traceability all the way down to mission traceability matrices, parts lists, master equipment lists, all the whole thing. And a lot of these studies also talked about trades and why they ended up at the architectures that they did, and the things that were learned that drove us to one architecture or another. And those kinds of things are going to be the most useful in going forward when designing the actual realizing these mission concepts, which were prioritized by the Astro 2020 Decadal Survey. And again, this allowed for more accurate mission cost and schedule estimates. Okay, so I'm going to focus mostly on LUVOIR and HABEX. I'll mention briefly Origins. I won't have time to talk about Lynx, but all 4 have some exoplanet applications, but LUVOIR and HABEX are sort of the ones that have the most fraction of their science dedicated to exoplanets, in particular direct imaging and characterization of nearby exoplanets. So we got asked a lot during the course of these studies, what is the difference between HABEX and LUVOIR? And so we came up with this slide, the teams worked together, came up with this slide to present to the public. So we devoted, the science that was targeted by these 2 mission concepts was broadly very similar. So there was general astrophysics science in the kind of sense of the next generation Hubble, but then there's also the direct imaging of exoplanets. And together, these 2 mission concept studies presented 11 different architectures. And the idea was to provide a buffet of options to the Decadal Survey, understanding that they weren't going to pick any one of these individual architectures, but we're going to pick, some notional thing somewhere in between. And we really wanted that decision to be as well informed as possible. And so not surprisingly, they ended up prioritizing a 6 meter, which was between the smallest LUVOIR design and the largest HABEX design. And both mission concepts emphasize that the exoplanet science and the general observatory science was equally important in terms of the vision of what these missions could do. So very briefly, I don't want to talk too much about the architectures because again, these are no longer a thing, right? There's no more HABEX, there's no more LUVOIR, but there is some important things to learn from because of the architectures that we settled on and why we settled on those architectures. So HABEX was more conservative by design. So we came up with a 4 meter off-axis aluminum coated monolithic mirror. Monolithic because that makes coronography a lot easier. Again, off-axis because coronography is a lot easier. We had 4 different instruments. We included not only coronography to block the light from the star, but also star shade. Those turned out to be very complementary. And I'll talk a little bit about that in a second. And the 4 meter was our notional, but we studied a bunch of different smaller architectures as well. One of which was actually studied in more detail by Aerospace during the Astro 2020. So I can talk about that in a little bit. So these are the 4 instruments that we came up with, and these are their basic properties. I won't go through these in detail because again, these are kind of notional, but there's reasons why we settled on all these numbers. And some of these were to do with science, a lot of this to do with science, but it was also science informed by technology and risk. And so I think, reviewing how we arrived at these decisions is going to be important going forward. I don't have time to go into all that. One important thing is, why a coronagraph and a star shade? Well, they're very complementary starlight suppression techniques. Chronograph is nimble because it's on the telescope, so it's very good for blind searches and orbit determination, but chronographs are inherently chromatic, and so you get narrow instantaneous band passes, which means unless you have multiple channels in your chronograph, you have to build up the spectra sequentially. And they typically have a limited outer working angle, and they're not good for obscured primaries, on-axis primaries. Starshade, on the other hand, has a very wide instantaneous bandpass because it's essentially achromatic, has a very high throughput. You can get very deep nulls, large outer working angle set by the size of your detector, small working angles down to sort of lambda over D, so maybe half of what you'd expect from a chronograph. And as such, they're very good for spectral characterization. Problem, of course, is the star shade is enormous. It's flying about, in the case of HABEX, it was 52 meters, flying 75,000 kilometers away from the telescope. And the stars are obviously that you're looking at are located all over the sky, and it takes about 2 weeks to slew from one star target to the other. And then, you have a limited number of slews because of fuel. So it's really good for once you find a planet that you really want to characterize very well, then you can point your star shade at it. And so HABEX had this kind of hybrid structure where we would find the interesting systems using the chronograph and then follow them up using the star shape. Okay, and then LUVOIR was much more ambitious. There were 2 LUVOIR designs, A and B, a 15 meter and 8 meter. These are circumscribed, not inscribed. I'll describe the difference here in a second. Similar wavelength range as HABEX, although a little bit broader. With the larger aperture, you can go out to longer wavelengths, even though the thermal emission from the telescope is starting to ramp up just because you have such a large aperture and getting so many photons. And both of these mission concepts were designed to be serviceable and upgradable, and have 5-year mission durations, 10 years as consumables, but really with an eye of being multi-decadal missions. 4 instruments as well for LUVOIR. 3 of them map it very closely to 3 of the instruments on HABEX. One of them is very unique, which is Pollux, a UV spectropolarimeter. LUVOIR did not consider in detail a star shade, and therefore did not have a star shade instrument. Now, I think that's something that should be considered when going forward with the 6-meter telescope. The Twiddle 6-meter telescope design. Okay, now on, I'll just sort of lump LUVOIR and HABEX together. The obvious science goals in terms of exoplanets is to survey the nearest stars for potentially habitable worlds. And the number of those depends on what aperture you're looking at and what design. So dozens to hundreds, depending on the aperture that you're looking at. And the idea is that you want to find things that look like they might be in the habitable zone, measure their orbits to see if they actually are in the habitable zone, and get maybe phase curve information so you could distinguish them from dust clumps that are orbiting at similar separations. And then you go and you spend, on the best candidates, you spend your time getting the spectral characterization to look for potentially habitable conditions and maybe biosignatures as well. So that's the basic concept of how this is going to work. And this just shows simulated images from the Habex coronagraph and the LUVOIR coronagraph. Obviously, the LUVOIR coronagraph has a much smaller inner working angle. And then this is obviously what we would like to see. So this is a simulated spectra of beta CBN, which is a G0 5-star at about 8.4 parsecs away. This is assuming 230 hours of observations with Habex. It would be less with LUVOIR, but this is the kind of signal to noise and resolution that we baselined for this system. And so you can see Rayleigh scattering, you can see oxygen, you can see the ozone cutoff, you can see water. One thing there's lots of things to think about in terms of resolution and signal to noise and wavelength coverage. But one important thing is that we really want to get the oxygen, the UV coronography to get to be sensitive to ozone. And that's because in, for example, Proterozoic Earth, which was definitely habitable and inhabited, the oxygen level was much smaller, and depending on where you are in that era, and as a result, the oxygen line is very hard to detect. But the ozone is much easier to detect. So you really need UV high contrast imaging, and that's difficult in general with a coronagraph, but it's probably easier with a star shade and doesn't require a bigger star shade. And so it might be that with a 6-meter telescope, while that might be too big for a full-fledged star shade, it might be good for a UV star shade. So that's just one example of a trade that needs to be considered going forward. And in terms of yield, obviously LUVOIR A and B are going to be a lot more than Habex. So these are the yields for LUVOIR A and B in blue and green, and then in Habex here in gray. And so the exciting thing about these missions is, we're not just going to get potentially habitable planets located in the habitable zone that are roughly the size of the Earth. We're going to get planets with a wide range of masses and radii and orbits that we can characterize and do comparative exoplanetology, which is super exciting. But for the habitable planet candidates, the yields for LUVOIR A were 54, LUVOIR B 28, and Habex 8, with substantial uncertainties, of course. Although in all three cases, the probability of not being able to characterize any habitable, potentially habitable planet candidates was extremely small. And so these are kind of the yields of all kinds of planets with characterized spectra. All right, so I'm actually sort of running out of time. I don't have a lot of time to talk about origins, but one of the big science cases of origins was transmission spectroscopy, as again, I'm kind of preaching to the choir here, with the idea that it has a broader wavelength coverage than JWST and would have better control of systematics due to detector noise because of the more advanced, detector technology as well. And so you would expect here, this is the transmission spectroscopy signal that you would get of a temperate terrestrial planet around low mass stars after building up many transits. And if you compare this to the JWST simulation, you can see that many of these features are much cleaner and easier to detect. And of course, you have a much longer wavelength coverage with the notional origins design. Now, what actually gets prioritized or happens is up in TBD. And then finally, I don't have time to talk about this, but there's large interferometer for exoplanets or life, which is a 10-micron thermal emission mission to directly detect and characterize Earth-like planets around Sun-like stars, but in thermal emission. That gives you access to radii of these planets if you can combine it with detections with LUVEX, but also a different range of chemical species in the atmosphere where you have absorption in the near infrared or the mid-infrared. Okay, so last few minutes, I'll just talk about the decadal survey. I think we're mostly familiar about what came out of this. Overall, I think very good news for exoplanets. So the main thing that was prioritized in terms of large space-based missions by the 2020 decadal survey was actually what we're calling the GOMAP, which was a mission and science and technology maturation program, which I'll talk about in a second. But in terms of mission concepts, I think it's reasonable to summarize that basically all of the large mission concepts that I mentioned were prioritized, although not at the same time and not exactly as imagined by these large decadal surveys. So I'm calling these the new great observatories, with the first one being a LUVEX kind of 6 meter, and then later on something like an Origins, and then something like an X-ray. And so there's a lot of interesting things about this decadal survey, but I think one of them that's worth noting is it was very much, as they call it, a pan-decadal survey. It wasn't just focused on the next 10 years. So here's this main recommendation, the Great Observatories Mission and Technology Maturation Program, which was very much advocated by a large mission studies report by National Academy of Sciences, and adopted by the 4 large mission concepts as an extended pre-phase A activity where you do your trade studies and develop your technologies in great detail in order to buy down cost and risk when you actually start with the mission development in phase A. And this was thought to be, and is thought by those of us that did the mission studies, but also agreed upon by the decadal survey to be crucial to make sure that we can build these things on time and on budget. And so this would be a sort of 5-year mission, 5-year phase where the science and technology maturation program would happen before the first decadal, the first mission, which would be this 6 meter IRUV, what do you want to call it? And so this priority has been a little confusing to some of the people in the community, just because it's not a mission per se. It's a mission technology and science development program, but once you understand the reasons behind it, it makes a lot of sense that this was the main priority. And then the first of the large missions would be the 6 meter, what we call LUVEX. I just want to emphasize, this is not LUVOIR. So people have, I've heard all of these things before. This is not LUVOIR. This is not HABEX. LUVOIR didn't win. HABEX didn't win. It's really something that's imagined to be a hybrid or somewhere in between the two of them, and as evidenced by this quote from Julianne Delcan, who's on the steering committee. So I like to call it LUVEX because all the other names that I've heard proposed are terrible, but we're still waiting for a new name from NASA headquarters for what this is called. And they have detailed justifications. I'm running out of time. I'm not going to go through these, of why 6 meters was the optimal aperture. And so it was a trade between cutting edge geoscience and yields of exoplanets, and cost and schedule and risk on the large end. And so 6 meters was considered to be kind of a sweet spot with a yield of roughly 25 habitable zone planets. All right, let me skip that. I'll skip that. If you want to know what 6 meter means, we can talk about it. I think it's extremely important. People are already getting wrapped around the axle in the 6 meter, the 6 number. 6 meter had a twiddle in front of it that was very intentional. This could easily end up being 5 meters or 7 meters, or even something more different than 6 meters, depending on the science and technology trades that need to be done. And I think it's important for people that are thinking about this to think about their science, be it exoplanets or not, and think about breakpoints in terms of aperture, where you can start to do science that you couldn't do before, or if the aperture is slightly smaller, important science falls away. So for example, if you had an 8 meter, you can already get out to the nearest giant elliptical to do resolved stellar populations, but with smaller apertures, you wouldn't be able to get out that far. So that's an example of a breakpoint. And in terms of the timing, this is the sort of Gantt chart from the survey. This is where we are. We have a 5-year GOMAP phase, and then before the next decadal survey, there would be a review of the GOMAP process to see if we're ready to start phase A for the 6 meter UV optical infrared telescope. And there's a substantial amount of money for this GOMAP. So this is important that we figure out what needs to be done and do it right. Okay, so this is what I think we should do now. Realizing this mission requires a significant increase in the NASA budget. So those of you that can lobby for more money for NASA astrophysics, I encourage you to do so. We need significant advocacy to do this. There's a lot of precursor science work that needs to be done, as well as technology development and other things as well. What needs to be done? Well, I don't think we know, but we should figure it out real soon. And as part of the process of figuring that out, we have a number of meetings and sessions coming up. So just next week, there's the NASA Precursors to Pathways. meeting. This is April 20th to 22nd. It's hybrid. I encourage you to attend that. We've gotten a splinter session in the Exoplanets 4 meeting about future comparative exoplanetology with the large mission concepts and the ELTs. And there's a splinter session on the new great observatories in the summer AAS that's also been approved. So I encourage you to get involved. And with that, I'll say thank you, and I'll leave up this slide, which just shows the amazing prospects that we have for future exoplanet missions and telescopes.
Thank you so much, Scott.
Apologize for going over.
Oh, no, that was great. That was great. It was great to see an overview of everything from someone who's been on the ground for it. So thank you so much. So yeah, we have time for some questions or discussions. If anyone wants to raise their hand or post them in chat, and I can read them. Looks like Estelle, do you want to go ahead?
Yes, hello. Thank you for your talk. That was great. I just had a question. So with beyond characterizing and better detecting exoplanets, I was wondering if this was going to go hand in hand with better surveys of stars and especially star variability, because we know this is going to have a great impact on what we get out of these missions in the end.
Right. I completely agree with that. I mean, the know thy star, know thy planet is very much of a zealot when it comes to that mantra. And, you know, I just didn't have time to talk about those things. But, you know, Gaia has already revolutionized our understanding of exoplanets, primarily through our understanding of the stars, not the exoplanets themselves. Although Gaia will tell us about exoplanets and is already helping us find wide orbit exoplanets. And you know, I think we need to think pretty hard, in particular for this future 6-meter telescope, about what we need to know about the host stars in order to really get all this information out about the planets. You know, if you think about it, these 100 or so stars are going to be the most well-studied. I mean, they're kind of already are the most well-studied stars in, you know, ever, but they're going to be even more well-studied. And we're going to want to know everything we can about them. And so some open questions are, you know, do we need to actually figure out what planets are there before we go and target them? It's not required for the 6-meter telescope, but it might help make this survey more efficient. Do we know enough about the exozodi? Probably, but that should be thought about more carefully. Do we know about the variability of the star? As you mentioned, in particular, high energy variability. And that's kind of one of the science cases of LINX actually, was to characterize the high energy emission and variability of exoplanet host stars. And that's something where LINX could make a great contribution. So yeah, absolutely, this is super important. And I think that as part of this precursor science work that needs to be done, people should think hard about that. And during the splinter session we have Exoplanets 4, there's one talk that's going to be devoted to this particular topic.
Thank you.
Great. Does anyone else have any other questions for Scott? Go ahead, Avi.
Thanks for your slides, Avi. Oh, this is Avi, not Aki. Sorry, I do that all the time. Hi, Avi.
I think you're muted, Avi.
Yeah. Yep. You're not the only one, Scott.
No. Anyway, sorry.
No worries. Great talk. One thing that's come up quite a bit is thinking about how we actually do a survey of potentially or planets in the habitable zones of M stars, the atmospheres of these planets for a significant number of targets, of stars, of planets, frankly, because we know from a lot of the M star transit surveys that we're finding a small number of these systems like TRAPPIST-1. TRAPPIST-1, of course, is, you know, spectacular, but it's
right.
One system. And determining the sort of frequency of atmospheres and potentially habitability around these stars seems to, as we know from, you know, all the direct imaging studies for G-type stars, would take a lot of targets.
Right.
So how do we get to that point, and which mission, you know, will take us there?
It's good.
Or ground-based.
Yeah, it's a good question. So, you know, obviously with Origins or something like Origins, we'll be able to get down to the signal to noise that you need on on, you know, a larger sample of stars, I think. If you can,
Well, but it's not going to be any larger than JWST in this sense, and so you'll still have this many transit problem in
right.
that sense.
So I think I don't really know the answer to the question. I think, you know, ELTs will help us because we'll be able to characterize at least some temperate terrestrials around low mass M dwarfs with ELTs, assuming we can get down to the contrast ratios and adaptive optics inner working angle that is being promised. And you know, if depend on the larger side of the LUVEX, you know, there's a significant sample of M dwarfs actually in there. I don't actually remember how many, Aki. How many M dwarfs did you have in your sample?
Oh, I want to say a couple dozen.
Couple dozen. So, but yeah, it's hard sledding. It's not easy.
I only sort of raised that because there's so much discussion about it, obviously, mostly related to JWST because it will do a few, but there's not a lot of consideration of, you know, what type of sample and how do we get that sample to truly understand habitability around M stars.
I mean, there's lots of ways you can think about finding additional TRAPPIST-like systems that I think that are within reach, certainly in the next few decades. But, you know, can we actually characterize those planets and I think that's going to be very hard. So
Exactly. Interesting. Thanks.
Sorry, I was on mute. But Scott, this is not an easy question to answer, but I just wanted to hear your kind of thoughts and opinions when it comes to LUVEX and the decisions that are coming up and the design of it. From a science perspective, what do you think are going to be, you know, the real tough points? You mentioned a lot about a star shade and the presence of that being there or not. Do you think that's going to be a big decision point that's going to have to be made? Or are there other science perspectives that are going to lead into the design of this future mission that we should be thinking about right now?
I mean, yes, this is a hard question to answer. And you know, part of my answer is going to be, I don't know, but we should think about it and figure it out. I mean, it's part of the reason I'm giving this talk is to get people to think about these things. I mentioned a few things already. So hopefully this won't make Aki too mad. So A to Earth is something that we, you know, don't know super precisely. Do we need to know it better to design these missions? Probably not. But will we like to know it better? Almost certainly. Do we need to actually find the candidates around the nearby stars that we're going to directly detect? We don't have to, but it would be nice. It would make our surveys more efficient in general, although I think that's somewhat of an open question, and that's an aperture dependent statement. I think, you know, how do we get to UV high contrast imaging? I think that's an important consideration. Can we do UV coronography efficiently enough to do this? And if not, should we then consider a star shade, a smaller star shade? Those are important things. I think the whole trade of wavelength coverage versus resolution versus signal to noise needs to be revisited. I think a lot of great work has been done on that, and it's, you know, it's probably basically the right answer, but we should probably think about it more, especially when we start thinking about things that are not exactly Earth now, right? So when we start thinking about Proterozoic Earth or Archean Earth, or things that are not neither of those that might be habitable or inhabited, you know, are the requirements for signal to noise, wavelength range, and resolution the same, are good enough? And, you know, I think people like Sean and Giada have opinions on this already, I suspect, but I think they would agree with me that more work needs to be done on that kind of stuff as well. I think, you know, one thing is, I think we need to develop a somewhat more holistic idea of what we're doing when we're trying to detect and characterize Earth-like planets, because, you know, the whole idea of A to Earth and looking for water and the oxygen line and ozone, you know, is very focused on this one specific example of what we think a potentially habitable planet looks like. Whereas what's actually going to happen is we're just going to take spectra of as many small things somewhere in the neighborhood of the habitable zone as possible, right, and define the habitable zone empirically. And so that, I think, you know, probably calls for a somewhat different survey strategy and maybe different instrumentation, at least somewhat different instrumentation than this very sort of specific narrow goal that we use to kind of optimize these architectures.
Sounds good. All right. Does anyone else have any other questions or discussion points for Scott? It looks like there's general agreement with you in chat. All right. Well, if not, then we are pretty much up at the hour. Scott, thanks again for coming out and talking to us. This was really, really great to see the overview of this, and excited to see where we go.
Yep.
And thank you everyone for coming out today. Our next talk is going to be by Tom Evans on April 28th, talking about biosignature detection with JWST. And thanks for everyone for coming out again. Take care, Scott.
Thanks.